Welcome to radar system course. Today we continue the discussion on FMCW radar. So FMCW radar means what? It is about a frequency modulated CW radar. So we have seen that a CW radar in which the issues related to the bandwidth was there, and because of that it error bandwidth, so sensitivity of a receiver decreases there. And again, when we supposed to send a signal to the target, then we supposed to know that the timing of the waveform. What will be the start time, at what time that signal is to be sent there, so that we require to measure the range between the target and a radar there. Then again, one more issue is about that because of a narrow bandwidth, so we have a limitations regarding the spectrum, and then we need to work within a particular spectrum there. If we suppose to increase the spectrum, that is a broader one, in that case, so there will be the limitation at the receiver, and then there will be the range for the, there will be the a signal to noise ratio at the receiver. So to improve the spectrum, or we can say that broadening the spectrum there, so then we can use only, instead of a CW radar, we can use a modulated modulation there, or whatever the spectrum is supposed to consider at the at a transmission, that spectrum is to be a modulated one. So we have a scope of modulation either at amplitude, or we can modulate a signal based on the frequency there or a phase there. So we have a scope here, amplitude, frequency, or a phase modulation there, and using the modulation we can send a signal there. But if you consider that a amplitude modulation, then what happened? That pulse is to be a narrow one, and but we can do the accurate measurement using that a amplitude modulation. But then they have some limitations for the spectrum, because we need to consider that in arrow pulse, and then that is to be transmitted. So that's why there will be the limitations about the spectrum there. Again, another issue we will get through that, that's about the timing of a transmitting signal and all. So instead of that, we are supposed to use a frequency modulation here to transmit the signal. So that's why frequency modulated CW radar, the name is there because it will use a frequency modulation there, and due to that frequency modulation we easily increase the spectrum, or we can use this FMCW radar for the wideband application, because that CW radar is about a frequency modulated, means your carrier will be of a frequency modulated there, and then when it will be of a frequency modulated, so timing mark, if you consider at what time your signal is started, so instead of that, the timing mark is based on the frequency there, means what will be the variation in the frequency there that is occur with a particular period of a time, and that difference of a frequency means what, at a transmitting frequency and the echo frequency signal, so there may be a small difference in the signal there, and that will define you the what will be the a transit time there. So just like we say that generally from the radar, okay, we have a radar here, and for the radar we supposed to send the signal to your object. That object may be of any object there, so we supposed to receive the signal, that is about the echo signal from the object or a target. But which portion of the echo signal is to be considered? Okay, that will decide there. And this one is about your transmitting frequency signal ft, and this one is about your echo. That is about, we supposed to say that this one is about a received signal. Now that ft and fr, they have small difference. Why this will be, there will be a small difference? Because there will be the issues of what we can say that echo signal received at the receiver, okay, at the radar receiver. So there will be a small difference in the frequency between the transmitting and receiving frequency there, because we supposed to use a frequency modulated carrier. So that's why there may be a small deviation in the transmitting and the receiving echo signal. If that deviation will be larger for a given time interval, then we are able to measure the accurate transit time, and then we can utilize a large spectrum there. Okay, so means we can say that for the measurement, generally we say that a signal is to be transmitted here, and then we supposed to measure the, what will be the a time, or you can say that a transit time. Transit time is for between the transmitting and the receiving signal. So in the case of FMCW radar, so there will be a frequency modulation. We supposed to consider that frequency modulation will be a linear. In that case, a frequency is increases, okay, linearly, and then this one is about your transmitted signal. Okay, we can say that this one is about a frequency, and this one is about a time. Your signal frequency is increases, okay, that is about a linearly, and at the same time, okay, so we supposed to receive the echo signal, and in that case we are receiving the echo, and that echo, if you consider, there is a small difference in the frequency. Okay, there is a small difference here. So that's why we can say that that frequency is called as a bit frequency. And this transmitting and a receiving section, if you consider that, so that much in terms of a time, so that will be the t, that is nothing but a transit time for transmitting and a receiving echo. So it will be it will define you what will be the range of a object from the radar there. C is equal to 3 into 10 power 8, and twice is nothing but what, a round trip distance, and that r is nothing but the range between the radar and the object there. Now we can consider here what will be the difference in the frequency signal here, because we say that the transmitted frequency we have, it is linearly changes with respect to time. Okay, means we if you see that, observe here, so this transmitting frequency that is about shown in this line, so this one is about your transmitting frequency signal, we say here. Okay, this one is about a transmitting now, and this one is about what we can say a received signal. Okay, or you can say that a echo signal. Now the transmitting frequency signal it changes with respect to time. Similarly, we have a receiving frequency signal. Okay, that is again changes with respect to a time. Now there is an object. Okay, there is an object, and that object reflecting that echo. That's why we are getting the a time that is called as a transit time, because from the transmitting to the receiving, okay, that echo will be returned. Okay, so that's why we can say that t is equal to twice r by 3, and this is nothing but what we can say a echo signal here. Now our aim is about to find out, so what will be the a bit frequency here. If the target is about a fixed one, if the target is about a fixed one, there will be small deviation in the frequency, for the transmitting and receiving there. But if the target is a moving, okay, if the target will be moving, then there will be a Doppler shift of the frequency. So in that case, we observe that a bit frequency signal plus or minus what will be the a Doppler shift is there. So means a total frequency, if you consider here, so what will be the a frequency of observation here? So in that case, we supposed to know that what will be the a transmit frequency and a receiving frequency there with a respective that a time there. Whether we supposed to use a transmitting signal that will be a triangular, okay, whatever the what you can say that we have a signal frequency, or we can consider that whether it will be of a sawtooth fashion, okay. So in generally, if you consider that there will be a triangular frequency modulation, or we can say that there may be a sawtooth, or there may be a sinusoidal modulation, okay, like so we have a signal, okay, and that signal will be what we consider that there will be the a bit frequency, and that bit frequency is depending upon that what will be your transmitting frequency signal and what will be the time there. So for example, if I supposed to be consider here, this one is about your frequency here, okay, and if supposed to be that frequency is about a up one, okay, upward one, upward chip, okay, it is about a increasing order. So then how it looks like your your signal looks like here, because it is about up here. So we supposed to consider that a frequency will be increasing like that. Okay, so amplitude is a constant, okay, so this one. But if we consider that there will be a down here, okay, with respect to time, frequency will be down with respect to time. So in that case, your signal will be looks like, okay, so amplitude will be constant. So then what will be the a continuous carrier here, and that carrier will be modulated by a periodic function. That periodic function, whether it will be of a sinusoidal or a sawtooth, or what, whether it will be a triangular one. So whether what will be your transmitted signal there, okay. So according to that, we supposed to receive the signal that will be of a triangular one or in a sawtooth fashion. That's why we can consider here what will be the periodicity in a modulation, whether it is a sinusoidal or a triangular one. So based on those, based on the periodicity of a modulation, so we can consider that a triangular modulation or a sawtooth modulation there, and then for this particular modulation or that shape, that is triangular or sawtooth modulation, so sawtooth shape will be there. For that particular modulation, there will be the a bit frequency, and that bit frequency is nothing but what, that bit frequency is nothing but a difference in the transmitting and receiving, but that bit frequency is a function of time. So we can define a bit frequency that will be a function of time. So in that case, we can write here the bit frequency is equal to what will be the time here. Okay, what will be the time here? With respect to that, what will be the change in the a carrier frequency? Okay, what will be the change in the a carrier frequency? So that will be defined a what will be the a bit frequency. This will be nothing but the a bit frequency. Or we can say here bit frequency is nothing but what we can write a change with respect to, or this one we can write. Okay, this is about the rate of change of the carrier frequency f0 here. Or we can define that the bit frequency in terms of what will be the modulation period or a modulation frequency there. Okay, or we can define in terms of a what will be the modulation bandwidth. So generally we supposed to consider that a bit frequency is nothing but what, this one is about a time, is about a time means what, a transit time, or we can say that a two-way propagation delay means at a time for a transmitting signal to the receiving signal. This one is about a time here. Okay, this is called as a t here. Okay, and then that will define you. Okay, that will define you the a bit frequency, and that f is nothing but what, a carrier frequency we have. Okay, f will be nothing but a carrier frequency. Now, for the given particular frequency here, what will be the frequency sweep bandwidth here, and what will be the sweep time? Okay, what will be the sweep time? So that will define you. Okay, that sweep time is what, we have the a time here. So this is nothing but a sweep time. Okay, complete time, and this one is about your a bit frequency there. And that sweep time and that bit frequency, that will define you the what will be the difference in the that signal there. Okay, so now we need to know about here what type of a modulations we have, whether it will be sawtooth or a triangular. So according to that, that bit frequency will be changes. So instead of writing in this way here, so we can write here bit frequency here with respect to a carrier here. So we can write, instead of a carrier, we can write what will be the modulation bandwidth and what will be the modulation period. Okay, so simply we can write in another way here. So that is about a bit frequency is equal to, with respect to a twice r here divided by c, and that will be what, delta f here. Okay, so this one is about a delta f, that is about a modulation bandwidth, and we can say that a modulation fm frequency. Okay, for the modulated frequency fm here, or we can say that rate of a modulation. So we can define fm is equal to what, 1 by modulation period also. Fm is equal to what, 1 by atm. So this one will be the equation, and that equation in which this one is about a factor for your time propagation delay time, or this one is about t is equal to twice r by c, or transit time from transmitting and a receiving signal. And this way we define here the fb. Okay, this way we define here the fb there. And this fb here, this one is the equation for what, for a fmcw radar equation, and that defines the a bit frequency and a what will be the a range here. This one is about for the range, and this one is about your related to your frequency here. Now we say here the bit frequency is nothing but what, is it is nothing but the a product of what will be the total frequency deviation there. Okay, what will be the total frequency deviation with respect to the a modulation period and a transit time. This one is about a bit frequency. This one is about a transit time or a time here. This one is about a difference here or a deviation in the frequency, and this one is about nothing but a modulation period or a modulation frequency, and that is nothing but a bit frequency. So if you consider here from the observation, we supposed to see the transmitting signal, and we supposed to get the receiving signal, that is about a equation. Now in terms of, if we assume some particular frequency here, okay, so what will be the, suppose if you consider that some assumption related to the bit frequency here, we can calculate the range, or we can calculate through all these what will be the a bit frequency there. If you consider that the waveform, okay, is that modulation waveform here, that will be of a sawtooth one, and that sawtooth waveform of a period Tm here, and its modulating frequency is Fm here. So in that case, so bit frequency equation for the sawtooth will be here. This one. This one will be work for the a sawtooth one. And if you consider that if the modulation type, okay, if the modulation type, if it is a triangular one, okay, if it is a triangular one, so in that case there will be sawtooth means what? Just like we have, sorry, sawtooth means, to consider here, just into this, okay, this one is the body sawtooth. But in the case of a triangular, okay, in the case of triangle you input, so in that case, if you consider that this particular portion increases, that is the body up, we can say that up chill, this one is the body down. So in that case, so that's why in this particular equation there will be a twice factor, okay, addition of this. That's why there will be a twice factor here. So we can write here, instead of it 2 here, so we can write this one is about a 4r by c here, and then this one will be the delta f, and one will be a fm here. And that frequency we consider here, this one for the delta f. Now what will be the delta f here? So delta f, if you consider here for a sawtooth now, okay, if you just remember this equation now, I'm just going to draw here what will be the a sawtooth notation, okay, in that particular case. So I suppose to draw a sawtooth waveform now, okay. So this one is about your transmitting signal, okay. For example, instead of sawtooth we can consider the this one also, okay, triangular also, okay. So this one is about for a sawtooth one, okay. Now this one is about your transmitting signal. Now the echo, this one is about the echo. Now this particular echo here, the deviation in the from this to this, that is nothing but a delta f, okay. Deviation is nothing but what will be the change in the frequency, this one and this one, that will be nothing but a delta f. This one is for the a sawtooth. For a triangular case here, if you consider that it will be a triangular one, this is about a transmitting, okay, this one is about a transmitting signal, and then we have the echo here. Now what will be the deviation here? So deviation is nothing but what? From this to this here. So that is nothing but the delta F. Okay, this is nothing but a delta F. Now this delta F and this FM modulating frequency, and this one is about a range that will define you the a bit frequency. And if you observe the a bit frequency for the same, okay, this one is for the sawtooth here for the same diagram, consider that what will be the bit frequency here. Bit frequency at this particular point of time here, so there will be the variation there. So you can consider that there may be the likewise at this particular moment. Now this is nothing but a beat frequency, or this is nothing but a beat frequency FB here. Okay, because FB is nothing but the difference in the transmitting signal and the receiving signal, or you can say that A equal here. That is about a beat frequency. Okay, and this one is about your triangular one. Now using this, we can find out the bit frequency. This is for the sawtooth, this equation is for sawtooth, this one is for the a triangular one. So I two terms will be added. Now we will go ahead here. What will be the block diagram for the FMCW radar, and then we will discuss about that what will be the Doppler effect on the FMCW radar. Okay, first of all, we continue here with the block diagram of a FMCW radar, and then we discuss about the what happened, or what happened to if there will be the target is a moving one. So just see the block diagram first. This one is about your FM transmitter. It's about FM transmitter. Then we have modulator here. Then we have at the receiver side, we have a separate receiver now, receiving antenna, and then receiving antenna, there will be the mixer first. After that, there will be the amplifier. Then for the mixer, one reference signal. Okay, this one is about a reference signal. That is about a reference signal from the transmitter. Then a amplifier. Okay, after that we have a limiter. Then frequency counter. This one is about a frequency counter here, and then this one is about a indicator. This one is about a block diagram of your FMCW radar there. Now from this FMCW radar, we consider here, so what will be the trip time? Okay, so what will be the bit frequency there? Okay, now we consider here first in this particular block diagram there. So we have a transmitter, that is about a modulator here. So we can consider that a modulation, it is about a FM1. Okay, so we can say that it is about a triangular or a sawtooth one. This one is about a transmitter block and separate antenna for the transmitter and receiver. Okay, so with isolation, keep the isolation, we supposed to have a separate component there, and there is a small reference signal we are providing, and that reference signal is to identify what will be the input signal. Okay, so what will be the echo signal? Generally, everything, if you consider what will be the difference of in the particular signal, for that purpose, supposed to use a reference signal at the mixer now. Now, after that, your signal is supposed to be amplified. So we can use the amplifier here because receiving signal is there, and that, or we can say that echo signal, when we consider that signal is about a small level there, so that's why we supposed to amplify that a bit frequency signal. And then after amplifier we supposed to use the limiter, and that limiter is used to remove what will be the noise or what will be the amplitude fluctuation here, and that will be removed by the a limiter there, and then we will get a particular signal or a cycle here, and from that signal we supposed to find out the what will be the a frequency here for the given particular signal, and then it will indicate that a echo signal frequency. Now in all the cases here, we consider first initial case that target is about a fixed one and a radar is about a fixed one. There is no motion. So in that case, a difference we can calculate that is about a small, and that small difference is nothing but the a bit frequency. That is about a difference in the frequency for the transmitter and receiver. But in another case, if you consider that we have a target, it is in a motion there. So then echo signal received at the receiver, there will be a Doppler shift in a frequency. Okay, there will be a Doppler shift in a frequency, or you can say that there will be Doppler effect, and that due to that Doppler effect, there will be a shift in the frequency of the echo signal or received signal, because that target is moving. So in that case, so what will be the bit frequency signal? The bit frequency signal is defined based on the velocity of the object there. Okay, so what will be the velocity of the object there, or a speed of the object there? So we consider here velocity of the object, and according to that we will define the bit frequency signal. So for example, it is about a sawtooth or a triangular one. For a sawtooth it is about a twice r. For the triangular it is about a 4r. Okay. So in that case, for example, I suppose to consider it is about a sawtooth one. So this will be a twice r by c here, and there will be a small deviation in the frequency, that is about a delta f, and there will be the fm here. Now this one is exactly the beat frequency, but due to the Doppler shift, then there will be changes in the frequency of. So in that case, this one will be the minus sign. This will be the, because what will be the velocity of the object here? We can define in capital terms here with respect to the y. Okay. So this will define you, or this will define you the Doppler frequency shift here. Okay. Because what will be the velocity of the target, this one v here, and that will define you the range, and that range will define in terms of a shift frequency or a bit frequency there. Because if you consider that a sawtooth one, there will be only one slope, and if you consider that a triangular one, there will be a two slope, up one slope and a downward slope. That's why we can say that alternate sweep of up and down. Okay. So if there will be the alternate sweep of up and down, then we can say that your triangular waveform, they have the bit frequency that will be the upsweep and a downsweep bit frequency, and that's why the velocity that will be again proportional to the that particular bit frequency there. So that's why for the triangular case we can define here the FB for what, upsweep, and FB for the downsweep. So we can consider that minus delta F. Okay, this one instead of a twice R we can define here a 4R by C. It is about a twice, first 4R, then a delta F into Fm. Then same, what will be the velocity of the object, and a C here. And that F0 is nothing but the a bit frequency here. Okay, F0, what we can say that it is nothing but the a bit frequency. Okay, and then that bit frequency means we can say that where we have, sorry, this FB is about a bit frequency, and F0 is nothing but what, whatever the a signal is supposed to be a transmitting. Okay, signal frequency. Now in this particular case here, that FB we are getting in this case, that will be for the a triangular in which there will be the upsweep, and FB for the downsweep will be defined. Instead of that, there will not minus 4, it will be a positive one, 4R. Okay, that slope by C. So delta F Fm plus twice of P F0 by C. Okay, so now we can define here for the given particular case what will be the change in the frequency there and what will be the velocity. So these two equations is for the triangular one. These two equations are for the triangular one. If it is upsweep and downsweep, upsweep, downsweep. Okay, so like, so for that upsweep and a downsweep, we got the equation here. So means we are getting that this one is about a range frequency here with respect to the a Doppler frequency. And if you consider that equation of FB with respect to the range frequency and a Doppler frequency shift, instead of this one we can write in terms of Doppler frequency shift here. Okay, so in that case your equation will be written into the form of FB up. We can write here in the form of FB up here, FR minus FD, and FB down, FR plus FD. This one is about a Doppler shift. Okay, earlier case you have seen that there is a minus sign, so that's why we have written here FR minus FD and FR plus FD there. And this FR is nothing but what, a range of a frequency. Okay, because there is the bit frequency up or a down, means you can say that for a FM cycle there will be difference between the bit frequency due to the a range frequency, that is about FR here, and there will be the Doppler shift. So we can find out here the bit frequency for up and bit frequency for the down. So from this equation we can find out what will be the range frequency, or we can say that range frequency obtained from this bit frequency. we can define here Fr is equal to what? 1 by 2. Okay, this one get cancel here, get cancel. 1 by 2 twice of Fr here, so it will be what? Fb up plus Fb down. Okay, that's about AFR. So here we consider that what will be the velocity of the object. The object, whether it will be reached toward the radar or away from the radar. So according to that, there will be the difference in the frequency there. And we consider that Fr and Fd here. Okay. Again, what will be the range frequency and what will be the Doppler frequency. So in that case, so what will be the difference in the modulation frequency here and what will be the Doppler frequency here? If that Fr will be greater than the Fd or Fr is less than the Fd. So in that case, we are supposed to find out that what will be the object position now, and through that we can find out that range of the object using this difference in the frequency there. So in terms of a graphical representation of this Fb and Fr, okay, Fb up and Fb down. So we can write here when we transmit the signal, okay, because we have a transmitted signal is about a triangular one. Okay, so this one is about your triangular signal now. Okay, in that case, we will get the echo here. We're supposed to consider that there will be the echo now. This one is about a received signal, we can say. And similarly, we're supposed to define that what will be the a bit frequency. So in this particular case, a bit frequency, because this one will be the up. Okay, this one will be the up now. This one will be the down. Will be the up. This one will be the down. So for the up, okay, for the case of up here, we can say that this one will be what? Fr minus Fd. And then we have the up now. This one. So this one will be the Fr plus Fd. So this is called as Fr minus Fd is nothing but what? Fb up, and this case is about what? Fb down. Okay, this one is about Fb up, Fb down. This is about Fb up, Fb down. Okay, so likewise, up, up, Fb up, Fb down. So Fr plus Fd or Fr minus Fd. And that will define you the difference in the whatever the range, and we can calculate that for a given target we can find out the range, or we can find out the velocity of the object. Okay, so we can write here again what will be the range of the object. So range of the object we can define, that is about a c by 8 del f into, we have the fm here, fb downshift minus fb upshift, okay, and the velocity is equal to minus c 4 f0 fb downshift plus fb upshift. Through that we can find out the range r, and we can find out the velocity there. Okay, so this one will indicate you the what will be the measurement, and all these measurement for the triangular modulation waveform. Okay, the waveform will be of a triangular model. With this, we stop here. Thank you all of you.